We're going to look at a few questions now, which looks at if a reaction is spontaneous or not. And in particular, we're going to only look at under standard conditions or standard state. And standard state is 1 molar concentration of reactants or of oxidant and reductant, a pH equal to 0, or in other words, that the H plus concentration is equal to 1, and 25 degrees Celsius or 298 degree Kelvin. So if a reaction is to be spontaneous, it is spontaneous if an oxidant, which has the higher reduction potential, standard reduction potential E0, reacts with or oxidizes a reductant, and that reductant must have a lower E0. In that case, the direction will be in the gamma direction and the reaction will be spontaneous. We can always get the change in the potential of the reaction or the potential of the cell, depending on how they ask you the question. So if we say potential of a reaction or a potential of a cell, it means that either they're in one pot or they're in separate pots. It doesn't really matter if they are in one pot or they're in separate places. You still get a delta E, or what we call sometimes only E0 of the cell or E0 of the reaction. And this is the E0 or delta E0 at standard conditions. That's always equal to the reduction potential of the reduction half reaction minus the reduction potential of the oxidation half reaction. When the delta E is greater than 0, that n, in other words, positive, we can assume that the reaction is spontaneous because the delta G, the free energy of that cell or that reaction, is at standard state is minus NF delta E0, and if the delta E is positive, this delta G is negative, and that means definitely it is spontaneous by the laws of thermodynamics. Once we have the delta E node as well, we can always get the equilibrium constant for the reaction, for the redox reaction, and the log of K equals N delta E naught divided by 0.592, where N is the total number of electrons transferred. Now, instead of N, sometimes you find it's in the form of N1, N2, or N times N prime, where each N is for different couples of a reaction. I like just to always see it in the form of just N, where N is the total number of electrons transferred throughout with the oxidant and the reductant. That's the only equations that you'll really need, and let's look at those. Number 2, explain why nitric acid attacks copper at room temperature, while sulfuric acid does not. Give the corresponding oxidation-reduction reaction in both cases. Okay, they give you the E nods for all the couples, and we're going to go right ahead. We place everything on a corresponding E nod scale, okay, and put all the couples that are involved. The NO2, NO couple, the copper, copper couple, copper 2 plus, the sulfate ion, SO2 couple, which with their respective E nodes, and put them in increasing order going upwards. The higher the E node going back, be my stronger oxidant or oxidizing agent, okay? So the NO3 minus, in this case, okay, which is the anion of nitric acid, and you all know that nitric acid is a strong acid which splits into H plus and NO3 minus. This ion and react with copper. And the reason it can react with the copper solid is that the reaction will be in the gamma direction. Now, the weaker oxidizing agent or oxidant is the SO4 2-, which comes from sulfuric acid, which is H2SO4, which is also a strong acid that can split and eventually gives me SO4 2-, though officially it just gives HSO4 2- at the stronger part of it. In any case, this weak oxidant cannot react spontaneously with copper, because if you look at it, it's in the form of the anti-gamma. Okay. Now, of course, also the nitric acid cannot react with the sulfuric acid because these are both on the oxidant side, and everything on the right-hand side is on the reductant side. Okay. Reductants can never react with each other, and oxidants can never react with each other. That's like a base with a base and an acid with an acid. There's no net reaction. Continue with an explanation. So we already decided on that we will have a spontaneous gamma reaction between the NO2 and the NO3 and the copper. And the delta E at standard state, E naught, is, or E naught of the reaction or E naught of the cell, depending on if they're assembled separately or not. I like to say the delta. In the course, we don't always put the delta, but it's actually good to put delta to mean the difference in the E naughts. So we have to decide who's the reduction reaction and who's the oxidation. And of course, it's an automatic. The nitrate is the reduction reaction. The stronger oxidant will remain in the reduction form of the reaction, and the lower E naught, which is the reductant couple, will do what? Will become the oxidation half reaction. Now, sometimes I can just put E naught of the oxidant minus E naught of the reductant, but I want to be consistent throughout the course, reduction minus oxidation, okay? So, and it's always like that, or cathode minus anode for cells. So we have the E naughts for each of the couples, and just put that right in. Now notice that we use the E naught as is with a minus sign, since the E naught for an oxidation is flipped. And instead of doing a flip for it, we just subtract the official E naught of the reduction minus E naught of the couple of the reduction potential, but for the couple that will undergo oxidation, but this is the E naught of the reduction potential. Subtract them both, you get 0.62. Now, if I want the reaction, I take the higher E naught couple and it will undergo a reduction. Let's see how. Keep them as is, the NO3 minus. I have to balance this equation because I need to have fully balanced half reactions. Add water to the side that's missing oxygen. I have 3 oxygens here. I have 1 oxygen here, so I need 2 water molecules. Then balance the hydrogen with H+, so I need 4 H pluses on this side. And then balance the total charge with electrons. So here we have a minus plus 4 plus. We have 3 plus on this side, we have 0 on this side, and so I need 3 electrons. Do the same, and notice indeed that this is a reduction reaction. Now for the oxidation half, what you go is like this. Copper goes to copper 2 plus. So start off with the copper, then the copper 2 plus. And try to get a balanced equation. Everything is balanced except the charge, and so I need plus 2 electrons on the product side. And you're pretty much done. But first we have to, before adding the 2 equations, balance the electrons on both sides. So we multiply the upper reaction by 2 and the lower reaction, the oxidation, by 3. Add the 2 equations and eliminate the electrons. You are done. Now notice in the nitric in the NO3, you see the acid form, the H+, which is actually really nitric acid. So if I was looking, instead of they giving me a couple, they gave you an actual equation, you would see that there's an equation which has NO3 minus with H+. Okay, so here's my global reaction, and that's what they asked for. Now, if they asked, and they didn't here, but if they asked for the K of this reaction, of course, we're expecting it to be spontaneous, and we notice that delta E is positive, and indeed, this is in the gamma direction, so which is, you know, logical. What would you expect the K to be here? Well, we have no idea. There's no expectations from the K because this is not a one-to-one equation. Now, if it were one-to-one, the K would be complete if the delta E is greater than 0.25. But it's not a one-to-one, so I have really no expectations other than a calculation. Calculate the log K. The total number of electrons transferred is 6. Why? Because 2 times 3 and 3 times 2. So, or you multiply simply, instead of n here, you put the number of electrons in the first couple multiplied by the number of electrons in the second couple. But if one is a factor of the other, then you multiply by only a factor. So I find it easier to think of it as the total electron transferred, which is 6. Multiplied by delta E, which is E reduction minus E oxidation, or simply 0.62. I could have just put 0.62 here, divided by 0.592. You must memorize this equation, okay? Of course, that's just 10. If I want the K, that's 10 to the power of this number. You could also memorize that. I find calculations to be a little bit easier with the log K expression. When the K, look at this K, it's absolutely humongous. It's huge, 10 to the 62. And therefore, this is definitely going to react in a complete fashion. The next part is they wanted you to, though this is in the anti-gamma, the reaction between the sulfuric acid, which is 4,2 minus in acidic medium, with copper is in the anti-gamma direction, and therefore it is not a spontaneous reaction. But they wanted you to write the reaction anyway. Okay? So if I want to do the reaction, I have no choice but the sulfuric acid be my oxidizing agent and my copper reducing agent. Why? Because I only have copper in my medium on this side, okay, on the right-hand side. So it's the only thing that could be reduced. Okay, so again, balance the oxygens with water. So get a balanced equation, guys. Go ahead, you do that. So here's my reduction, and my oxidation reaction is my copper becoming copper 2 plus 2 electrons. Add the two equations, you get a global reaction between the sulfuric acid. Notice there's an H plus with the sulfuric and the copper. Now, this global reaction, of course, has a delta E naught of E naught reduction minus E naught oxidation for everything. And the reduction half is, by assumption, the sulfate ion in acidic medium reaction minus the oxidation is my copper. So because I want to see if my copper is being oxidized. Okay, so they automatically are telling you that the copper is becoming oxidized. Okay, do the E naught subtraction. You get the delta E naught for this reaction is minus 0.17, and indeed that is negative and therefore non-spontaneous. But nonetheless, let's get the K value for it, though they didn't ask for it, but the log K again is this expression. Again, the number of electron transferred here, notice it's 2 on both sides, so it's not 4. Watch out. I don't multiply 2 times 2, okay? And that's why I don't like the n times n. I look at it, the number of electrons totally transferred in this equation is only 2. Okay. Delta E is this number minus 0.17 divided by 0.592. Look at the log K, get an expression for K. It's 10 to the minus 6. And can I really say that the reaction is limited? Well, I put it here, but I'm not really allowed to necessarily say that because it's not a one-to-one equation, but still you can assume probably that it is a limited reaction. But you know, it's not officially the case. I can't really, that's only the fact that 10 to the minus 6 or less than 10 to the minus 4 is limited is only for one-to-one equation. Okay, can silver be oxidized by MnO4 in acidic medium? And write the overall reaction. They also ask you to get the delta G of this reaction. Okay, again, let's put everything on a E0 axis. And again, everything here is under standard conditions because they didn't really give you any different concentration. So when they ask you, can something oxidize something else, and they don't give you concentration, assume that the concentrations are standard. So can the MnO4 in acidic medium, can silver, Ag, be oxidized by the MnO4? Okay, so can this Ag react with this MnO4? Okay, and the answer is, here's the delta E nodes, and indeed the MnO4 has a higher E0 value, and therefore it will remain undergoing reduction and will be my stronger oxidizing agent. And so the MnO4 will undergo reduction, and therefore the Ag here can undergo oxidation. And indeed, look at the MnO4 reacting with the Ag. Yeah, it's in the gamma direction. So the MnO4 can oxidize the Ag, or that the Ag can be oxidized by the MnO4 or react with. Anyways, continue with this, do the balancing, get the total number of electrons transferred, and that's gonna be 5 because you have 5 electrons on this side. So the total number of electrons transferred is 5. And here's my overall global reaction. Just try it. Make sure you know how to do that. Delta E naught for the reaction is E reduction minus E oxidation, which is actually the reduction potential minus the reduction potential of the other couple. Okay. So E naught of the manganese couple minus the E naught of the silver couple. So of course, guys, on an exam, you don't have to sit there and write E naught of this couple and write them in the form ox divided by red. Just E naught Mn, E naught Ag. Okay, you don't really, officially you should write it like that. That's the by convention, but on an exam, just put E naught Mn, E naught minus E naught Ag, and put the E naught for the couples. Ox divided by red. Okay, so 1.15 minus 0.8 is a positive number of 0.71, and indeed that is in the direction gamma, and it is spontaneous. Let's look at the delta G. What do you expect? Yes, you should expect it to be negative, and indeed, let's solve it. The number n here is for the total number of electron transferred, which is 5. Don't forget the minus sign for the delta G, minus NF delta E naught. In the books and in textbooks, and sometimes even in my class notes, I don't put delta E, you just see it as E naught cell. Okay, E naught of the cell, you have to have the word cell there, or delta E. Okay, get the delta E, you can go back ox minus red, or reduction minus oxidation, half reactions, or simply get this separately and put 0.78 for the delta E. Solve for delta G, and indeed the delta G will come out in joules, guys. Whatever number you get from here, because the Faraday's constant, go back to the units, is 96500 joules per volt per mole. So joules per volt per mole, or because joules per volt is coulombs per mole. 5 moles of electrons are transferred. The voltage is 0.71. That's V goes with the V. And you're left with joules. Now, if you see an answer in kilojoules, well, the answer should be divided by 1000 to get the answer of the delta G in kilojoules, and that's your number. Of course, it's negative.